Hi, this is my video number six. The continuation of the change of variable in multiple integral. Okay, so in this video, let me recall the sketch that we have done in my previous video, that we transform, if you remember, that we transform from just a minute. Okay, so we have that. Okay, we have transformed this the region S here, right? And the region R, this is X, Y, this is our R. Okay. We transform this region into UV plane, where we have our S is like that. Alright, this is S. Look at our previous example. Now, if you look at this two region, R and S, the area in this region R, area of R will not be the same as area of S. Whereas what should happen is that after we do the transformation, we might change the region, but in terms of quantity, in terms of area, it must preserve the area. Okay, so if we pick up a small area in R here, and we denote that as a del X, del Y, this small region here, this small region will be transformed into small region here, small area here. Let's denote that as a del U, del V. Okay, so in order this small region in R and this small region in S to be equal, or equivalence, so what we need to do, del X, del Y, we want to make sure after the transformation the area is preserved. So we have here del U, del V, del V. Okay, if just straight away like that, it will be wrong, because if you look at from here, definitely you can see clearly, the area is not the same. So in order to balance out, in order to make the area equivalence, we need to add some terms here. All right, these terms we call it as a Jacobian. Okay, so the purpose of the Jacobian here is to make the two region equivalence, to preserve the properties of the new region when we do the transformation. Now, let me give you the formal definition of the Jacobian. Okay, so the Jacobian of the transformation transformation T, say, given by X UV and Y UV, right, is del xy del uv equal to, we have xu, xv, yu, yv. Alright, where xu, yu, xv, yv is the differentiation respect to those subscript. Okay, so in this case, what we do is we transform from uv, to xy. In some region here in uv, we transform into some region here in ry. Okay, and we can also have if the transformation is given the other side, in the other way, yeah, u is a function of xy and y is a function of xy. Sorry, u is a function of xy and v is a function of xy. This is v, function of xy. So which means in this case we transform from xy coordinate to uv coordinate system. Okay, for this case, the Jacobian is given as, so this is the Jacobian, I put it J. Okay, here I can put it J. The Jacobian is given as del uv del xy, and this is equal to ux, uy, vx, vy. Okay, now since the function here ux respect to uv, y respect to uv, as well as u with the variable xy, v with the variable xy, these functions are continuous. These functions are continuous. We may have that del xy del uv is equal to the inverse of del uv del xy. Yeah, in practical, there is a case where we want to transform from a function coordinate xy to uv, but the transformation given in terms of function uv. So in that case, you need to do the inverse. Okay, so let's see the theorem, the related theorem for the double integral. Theorem. If you have we want to map a region S. We want to map uv, that's a region S, into xy, that's a region on xy, under the transformation T, and the transformation the transformation given is continuous. Yeah, so we have the x equal to x uv, y equal to uv, and they are continuous. Then if you want to evaluate the region R of x, xy, dA, that give us integrate f x of uv, y of uv, okay, and we need the Jacobian here, del xy del uv du dv. Okay, I think a little bit confused. So this should be the other way around. Should be that. Okay, should be that. From xy to uv. Now I'll give you an example. Let's say we consider the transformation from r theta plane. Consider the transformation from r theta plane, okay, to xy plane, r theta plane to xy plane, given by x r cos theta, y r sin theta. We have seen this many times. This is from, they do the transformation from rectangular to polar coordinates. Okay, so in fact I have shown this earlier when we solve one of the example. So in this case, the Jacobian del xy del r theta is given as xr x theta, yr y theta. Okay, so if you do that, so we have xr is cos theta, x theta is negative r sin theta, yr is sin theta, y theta is r cos theta, and then this will give you r. So thus we have, if you want to integrate, double integral over the region xy dA, under those transformation, so we may have, this will result to the region as f, our x is r cos theta, our y is r sin theta. The Jacobian, this is the Jacobian is r, so we have r dr d theta. Okay, let me give you another example how to apply the Jacobian, the transformation, everything in the double integral. Yeah, give me an example. Let's say we use the change of coordinates, change of variable, use x u squared minus v squared y to uv to evaluate integrate ry dA where r is parabola given by y squared equal to 4 minus 4x and y squared equal to 4 plus 4x. Okay, and x axis. Of course, in this case, I think you can. It is not difficult for you to try to sketch the old region and the new region after the transformation. If you look at that region R is given as what we have. Y squared is minus 4, so I think we have something like this. Alright, for that we have y squared plus, so we have something like this. This is I think here is 2, here is 0, so this is your R, and x axis here, so this is our R. Okay, and then you can find what is the transformation under this transformation. What is the region in U and V? Okay. So I leave it to you, that one. I think we have done this in the previous example, this kind of transformation, so you can look at that, how to obtain those region in UV. Okay, so what we need to do here is that we need to find what is the Jacobian. Okay, we need to find the Jacobian. Or first, I think I better write that under those transformation, what will happen? Under those transformation, this is R, our y, dA. Yeah. So basically from here, this is x. X is a function of UV, and y is a function of UV. Yeah, this. Okay, so under those transformation, what happened to the integrand here, and what happened to region that we are looking for? So this will become our region S, R, we change into S. Y, we give you a function of U and V, and our dA is, we have the Jacobian of du dV. So again, do not forget the Jacobian, you must take the positive value. Okay, so what we need to do now is we need to compute the Jacobian, we need to compute the transformation, we need to know the limit of integration. So that's why sketching here is important. Yeah, sketching here is important. If you do know how to sketch, then it might be difficult for us to determine the limit of integration. It is not compulsory, but it will help you to find the limit of integration. Okay, so let's evaluate the Jacobian. The Jacobian under that transformation is given as, we have xu, xv, yu, yv. Okay, this is equal to xu is 2u, 2v, yu is 2v, 2u. Okay, so we have 4u squared minus 4v, I think we should have negative somewhere. Del x del v, this should be negative. This should be negative. Okay, so we have plus for v squared. So if you look at here, this u squared, this is v squared, we have plus here, so this one is definitely positive, so you don't have to worry about the modulus of the Jacobian. So therefore we have our double integral ay dA, sorry, r y dA, that will give you double integral our y is here 2uv, so y is 2uv. This is under new region transformation. Then our Jacobian is that we have 4u squared plus 4v squared. This is the Jacobian. Then du dv. Okay, and the limit of integration you may find 0, 1, 0, 1. Okay, the limit of integration. So this integration from 0 to 1, integration from 0 to 1. So here you have 2uv 4u squared plus 4v squared du dv. So for this you should have no problem to evaluate this. I don't want to give detail, just evaluate one by one iteratively. I have explained to you how to do the iterative integral. Then I just give you the solution. We have that give you 2. Please check this. I hope it's correct. Now if you look at your notes, okay, you have an activity down there. So let us solve this activity. I still have a little bit time here. Just hold on a second. Let give you another example. So we want to evaluate this integral under R. E x plus y over x minus y dA. Okay, where R is given the region. R is a region with vertices. We have 1, 0, 2, 0, 0, negative 2, and 0, negative 1, 0, negative 1. And we may use the transformation. Here we have x plus y, here you have x minus y. Then from there we can straightly pick up the transformation. So let u equal to x plus y and v equal to x minus y. Okay, so if you plot this region R as well as S under that transformation, so for R we have xy 1, 0 is say here 1, 0, 2, 0 is here. We have 0 minus 2 and 0 minus 1. So 0 minus 2 somewhere here, 0 minus 1 somewhere here. So we have this region trapezoidal. So this is our R. Okay, this is minus 1 1 minus 2 2. I think you can find the equation for that straight away. This is y is equal to x minus 1. This is y equal to x minus 2. Yeah, it's not given, but you can find it. So under those transformation, if you do, I think you can get under that transformation, you may get what should I do this for you? So okay, so let's consider this as S1. Let's consider this S2, S3, and S4. Okay, we need to transform each of that boundaries into our new region. First thing, what happened to that integral under that transformation? So we have those integral e x plus y over x minus y dA, that will give you under that transformation. So we have this is under S, you need to find the limit for S, then x plus y, we have e, x plus y is u, x minus y is v, and you need the Jacobian du dv. Okay, so Jacobian here, the Jacobian there is should be, because here this is du dv, so we need to find the Jacobian del xy del uv. Okay, but the transformation given in terms of u and v, so in that case either you write xy in terms of uv, or you can find the Jacobian del uv del xy, and then you do the inverse. You can do that. So if you write this in terms of xy, I think it's not difficult. You can plus you got u plus v to x, so x equal to half u plus v. So do the transformation, rewrite those things. X is equal to half u plus v, and y equal to half u minus v. Okay, now you can find those Jacobian. So the Jacobian is given as, we have that is equal to, we have xu, xv, yu, yv, that equal to, if you do this, you got this is equal to half, and you do all the transformation, S1, S2, and S3. I show you one of them. x1 is x equal to 0, so y is moving from minus 1 to minus 2, so minus 2 to minus 1. Alright? No, sorry. Yeah, in this case, correct. And then y is from minus 2 to minus 1. Minus 2 to minus 1, right? So if x is equal to 0, so you have u equal to y, v equal to negative y. Alright? So that give you u equal to negative v. So that give you which line? U equal to negative v. U equal to negative v. So we have for that S1, this is S1 prime. and then you can find S2, S3. What you will find is that our S is given as that. This is 2, this is 1. You have S3 is here, this is S1, this is S2 prime, this is S3 prime, this is S4 prime. So this is our S. Okay, so to evaluate this, integrate this. Now we need to evaluate those. So we have, that's our integrand. S, our S is u from minus v to v. Alright, v from 0 to 1. V from 0 to 1. V from, sorry, v from 1 to 2, sorry. Alright, v from 1 to 2. U from minus v to v. So you have E u over v half our Jacobian du dv. So you have no problem to evaluate this. If you proceed this, you may have, that will give you 3 over 4 E minus 1. Alright. Okay, so I think that's all for this video. Or should I solve this? I think it's not difficult to do this. If you integrate this with respect to u, what you have, then it gives you v from 1 to 2. That one you have negative half, you can bring it out. This is integrate with respect to u, so you have 1 over v. You have 1 over v E u over v. Is that correct? dv. Okay, is it 1 over v? So you integrate that one, you have, I think that's correct. And then you can solve this problem. The left is 1 over integrate with respect to v, then that gives you much easier to solve. Alright, so thank you.